Hi everyone. Today we are going to discuss about decomposing a self-adjoint operator as a difference of two positive operators in a unique way. Before doing that, let us look at a known case. So let us start with a non-empty set X and f from X to R be a function. Now we can write f as mod f plus f by 2 minus mod f minus f by 2. We can again write f plus as mod f plus f by 2 and f minus as mod f minus f by 2, and these two functions f plus and f minus, these two are positive functions, and in fact the first part f plus is known as the positive part of and the second one is the negative part of. In fact, we can also show that mod f is nothing but f plus f minus by 2. Now we want to generalize this result to for operators defined on Hilbert space, in particular for self-adjoint operators. So let us start with let T be a self-adjoint operator defined on a Hilbert space. Now we know that T square is positive and we know that it has a unique positive square root. So we define mod T as positive square root of T square. We know that this is positive operator. So as in the earlier case, define T plus as mod T plus T by 2 and T minus as mod T minus T by 2. So the first one is known as positive part of T and the second operator T minus is known as the negative part of T, and it is easy to check that T can be written as T plus minus T minus. So T can be written as and mod T can be written as T plus T minus, and we can easily check that T plus into T minus equal to 0, that is T minus into T plus equal to 0. Next we want to show that these two operators T plus and T minus, they are positive. So we write as a theorem let T be a self-adjoint operator defined on Hilbert space H, then T plus and T minus both are positive. Okay. So let us look at the proof of this result. The proof of this result heavily depends on the proof of the square root of a positive operator. Let us quickly recall. If A is positive and bounded, So we assume that 0 less than a less than or equal to identity. So we have shown that a has a unique positive square root. So we have defined, we assume that a is between 0 and identity, then defined a naught is identity, a n plus 1 is a n plus a minus a n square by 2 for all n in n. And we have shown that 0 less than a n less than or equal to identity for all n in n. Of course, n union 0, and we have shown that a n converges to sum operator s at every point x in h, and this s square is exactly a, and this s is called as the square root of a. So s is now we are going to imitate the same proof to approximate mod t. In fact, from that we can get t plus. Okay, so let us look at proof of the result. So we know that when t is self-adjoint, t square is positive. So we can actually approximate t square instead of t. So the positive square root of t square is nothing but mod t. So let us define. So assume that the positive operator t square is between 0 and identity, and define tn plus 1 as tn plus t square minus tn square by 2. So in the earlier result we have used a instead of a square because we want to approximate square root of a, and we know that a is positive. In the present case, t square is positive, so we want to approximate square root of t square, that is mod t. So here also we can take n is n union 0. Let us call this as equation 1. So as in the earlier case, define t naught to be identity. Okay. Now we know that as in the earlier case, if we proceed, we get 0 less than tn less than or equal to identity, and tnx converges to mod tx for every x in h as n tends to infinity. This follows directly from the earlier result. Now we want to actually approximate t plus. So t plus is nothing but mod t plus t by 2. Hence we can actually write down Sn, define Sn as Tn plus t for every n in n union 0. Then we can easily show that Snx converges to mod tx plus tx, that is nothing but 2 times t plus x for all x in h. Now we want to actually show that t plus is positive. So the claim is t plus is positive. From this we can also show that t minus is positive. Okay. Now if we look at Sn plus 1, let us consider Sn plus 1, that is nothing but Tn plus 1 plus t, but Tn plus 1 we have a formula, that is Tn plus t square minus Tn square by 2, and this is plus t. Now Tn plus t is nothing but Sn, so this we can write as Sn plus t square minus Tn square by 2. Now here again we can write t square minus Tn square as t plus Tn into t minus Tn, provided t and Tn are commuting. So for the time being, let us assume that t and Tn are commuting, so we can write t plus Tn minus into t minus Tn by 2, that if Tn commutes with t for every n. Okay, so that means we can write down this as Sn plus Sn into t minus Tn by 2. So we can write this as Sn common I plus t minus Tn by 2, with the assumption that t and Tn commute. Now actually, to show that Sn or Sn plus 1 is positive, we use the induction process, mathematical induction. So if you assume that first we show that S0 and S1 are positive, and then once we show that, we assume that Sn is positive, from that Sn plus 1 we show that Sn plus 1 is positive. For that again, if we show that Sn is positive, and to get a conclusion that Sn plus 1 is positive, we have to use the fact that if we can show that Sn and these operators both commuting, and if we also show that this one is positive, then we have the result that product of two commuting positive operators is positive. From that we can conclude the result. Okay, so that is the idea of the proof. So our next goal is to show that t and Tn commute, and the second goal is to show that I plus t minus Tn by 2 is positive, and the third one is we want to show that Sn and the operator I plus t minus Tn by 2. Okay, so we want to show that Tn commutes with t for every n in n union 0. The second point we want to show is that I plus t minus Tn by 2 is positive for every n in n union 0. Third one is that Sn commute with I plus t minus Tn by 2. So these are the 3 points we want to show, and once we show that, we can conclude the result that Sns are positive. Since Sns are positive, we can conclude that t plus is positive. That is the overall idea of the proof. Okay, let us look at the proof of the first point. So when we take n equal to 0, t naught is identity. So n equal to 0 implies t naught is identity. So this implies t commutes with t naught. Okay. Now let us take n equal to 1. T1. If you look at by definition, T1 is by definition t naught plus t square minus t naught square by 2, but t naught is identity. So this is t naught plus t square minus t naught square by 2. This is t into identity plus t square minus identity by 2. This is t plus t cube minus t by 2. So we can take t common from the right hand side. This is I plus t square minus identity by 2 multiplied by t, and this is nothing but t1 into t. So we have shown that t and t1 commute. So in the same way, if you look at, if we consider t into t2, this is t into t1 plus t square minus t1 square by 2. So this is nothing but t1 plus t cube minus t1 square by 2. But by the earlier step, we know that t1 and t are commuting. So we can show that this we can conclude that this is t1 into t plus t square minus t1 square into t by 2. So this is t1 plus t square minus t1 square by 2 into t. This is nothing but t2 into t. So using the inductive process, we can actually show that t commutes with tn. So by the induction, we get t commutes with tn for every n in n. Okay. Now we know that Tsn is nothing but Tn plus T. So from this we can also show that, so this also implies that T commutes with Sn. Okay, so this completes the proof of the first statement. Now we want to show that the second one, I plus T minus Tn by 2. So let us look at the second part. So we want to show I plus T minus Tn by 2 is positive for every n in n union 0. So let us take T naught. T naught is identity. So we have I plus T minus T naught by 2 is I plus T minus identity by 2, and this is nothing but 2I plus T minus I by 2, that is I plus T by 2. Okay. So we can conclude that this is positive. The reason is that, so we have 0 less than t square less than or equal to identity implies norm t square is less than or equal to 1. This implies, since t is self-adjoint, norm t square is nothing but norm t whole square is less than or equal to 1. So this implies norm t less than or equal to 1. But as t is self-adjoint, so we know that minus identity less than t less than or equal to identity. So we have shown this result. If norm t less than or equal to delta, this implies minus delta I less than t less than delta I for any delta positive. When t is self-adjoint, we have proved this result. Okay, now you take delta to be 1. So from that we can conclude that minus I less than t less than I. But from this we can conclude that I minus t is positive as well as t plus I is positive. So from this we can say that, hence we can show that I plus t by 2 is positive. So we have shown that when n equal to 0, I plus t minus tn by 2 is positive. Now let us take n equal to 1. I plus t minus Tn by 2. So this we can write as I plus t plus I minus Tn by 2. So we know that I plus t by 2 is positive. This is I plus t by 2 plus I minus Tn by 2. We know that Tn's are between 0 and I. So we know that from this, so already we know that this is positive and we know that this is also positive. So sum of two positive operators is positive. So in fact we can actually show that for n in n we have this one, I plus t minus Tn by 2 is positive. So this completes the proof of the second statement. Now we want to show that Sn commutes with I plus t minus Tn. So the third statement, Sn into I plus t minus Tn by 2 must be equal to I plus t minus Tn by 2 multiplied by Sn for all n in n union 0. That's what we want to show. Now we know that Sn is nothing but Tn plus t, and we know that Tn commutes with t. So from that we can conclude that, so as Tn t equal to Tn we have proved in the first statement. The statement 3 holds true. Okay, so this completes the proof of the third statement. So we have shown that t commutes with Tn for every n in n union 0. I plus t minus Tn by 2 is positive and Sn commute with I plus t minus Tn by 2. And we have written Sn plus 1 is nothing but Sn into I plus t minus Tn by 2. We know that I plus t minus Tn by 2 is positive. Now from this we want to show that Sn is positive. The next claim is for every n in n union 0. So we have Sn plus 1 is nothing but Sn into I plus t minus Tn by 2. So let us take first we show that S naught is positive. So we have S naught by definition S naught is T naught plus T. So this is T naught plus T, this is I plus T. We know that this is already positive. Now S1 is nothing but S naught into I plus T minus T naught by 2. So we know that S naught is positive and this whole thing is positive. The product of two commuting positive operators is positive. From that we have already shown that Sn commute with I plus t minus Tn by 2. So we are using the result that the product of two commuting positive operators is positive. Now using this we can conclude that S1 is positive. Now the same way by induction, if we assume that Sn is positive, then from that we can conclude that Sn plus 1 is positive because of the same result. So hence okay, so we have shown that Sns are positive but we know that Sn converges to 2 times t plus. So if each Sn is positive, so inner product Snx with x converges to 2 times inner product t plus x with x, that is positive. So from this we can conclude that, so therefore we have limit now all the operators on the right hand side are positive, hence we can say that left hand side operator is positive. So from this we can conclude that t plus is positive. Now if you want to show that t minus, so t minus we can write in terms of t plus. So we have, if you look at minus t plus is mod of minus t plus minus t by 2. So this is nothing but mod t plus minus t by 2, because square root of modulus of minus t is that minus t into minus t whole power 1 by 2, that is t square 1 by 2, that is mod t. So we know that plus of any operator is self-adjoint operator positive, so we know that this is positive, hence we can conclude that t minus is positive. Okay, now we have shown that both the operators t plus and t minus, the way we have defined here, t plus is mod t plus t by 2, t minus is mod t minus t by 2, they are positive, and we are able to write t as a difference of these two operators, t plus minus t minus, and mod t is nothing but t plus plus t minus. And if you look at their product t plus into t minus, we can easily show that the product is 0. So next thing one can ask is that, is this decomposition unique? Suppose there exist positive operators A and B such that t equal to A minus B and their product is 0. Then we want to show that A is nothing but t plus and B is nothing but t minus. So then we have, look at t square, this is A minus B whole square, this is A square minus AB minus BA plus B square. AB is 0, hence if you take the adjoint to that, you will get BA is also 0, because A and B are positive, so you will get A square plus B square. So this implies mod t is nothing but A square plus B square square root. Okay. So this is mod A minus B. So this we can again write as A plus B whole square, and this we can write as A plus B, because square root of A plus B is positive, square root of A plus B whole square is A plus B. So we have t is A minus B and mod t is A plus B. Now from these two equations we can get A as t plus mod t by 2 and B as mod t minus t by 2. That means whatever the decomposition we obtained, that is unique. So t can be written as t plus minus t minus. Okay, so we will complete this lecture by giving an example. Let us look at a simple example. Let us take A, B are two real numbers. So define the matrix T as A0, 0B. Then we can easily show that mod T is nothing but mod A, 0, 0, mod B, and T plus is mod T plus T by 2. So you will get this as A plus mod A by 2, 0, 0, mod A, mod B plus B by 2. Similarly, we can show that T minus is mod A minus A by 2, 0, 0, mod B minus B by 2. This is for a matrix T. When it is given in this way, we know that T is a self-adjoint matrix, and in fact it gives a self-adjoint operator. Now let us slightly generalize this. Let us look at D from L2 to L2 defined by D of x1, x2, x3, so on. This is lambda 1 x1, lambda 2 x2, lambda 3 x3, so on, for all xn in L2, where this lambda n is a real sequence. In fact, it's bounded sequence. Okay, so we can write down this as a matrix with respect to standard orthogonal basis as the infinite diagonal matrix with diagonal entries as lambda 1, lambda 2, lambda 3, so on. And we can easily look at mod T, mod D as mod lambda 1, mod lambda 2, mod lambda 3, so on. Is an infinite matrix, and from this we can actually get what is D plus and what is D minus. So D plus is nothing but, so it is nth entry is lambda n plus mod lambda n by 2. So we get a diagonal matrix with nth entries lambda n plus mod lambda n by 2. Okay, so accordingly we can get what is D minus. So let us take a multiplication operator. So let us take y from L infinity of x sigma mu, where x sigma mu is a sigma finite measure space. So here phi is real valued. So look at the multiplication operator m phi from L2 of x sigma mu into L2 of x sigma mu. So m phi at f is phi f for every f in L2 of x sigma mu. We know that m phi is self-adjoint because phi is real valued. Okay. Now we want to look at the positive and negative part of m phi. So it is easy to look at positive part of m phi is m phi plus mod m phi by 2, but this is nothing but m phi plus m mod phi by 2. So we can easily show that modulus of m phi is nothing but multiplication operator induced by the function mod phi, and from this we can show that m phi plus mod phi by 2, that is the multiplication operator induced by this function phi plus mod phi by 2. This is m phi plus. Similarly, we can show that m phi minus is m phi minus, where phi plus mod phi by 2 and phi minus is mod phi minus phi by 2. Okay. So this way we can write down a self-adjoint operator as the difference of two positive operators in a unique way, and this decomposition sometimes is known as orthogonal decomposition of the self-adjoint operators. The reason is that we are able to get t plus into t minus is 0, therefore their product of t plus and t minus, and that means their ranges are orthogonal to each other. So for that reason it is known as orthogonal decomposition of self-adjoint operator. I will stop here. Thank you very much.